Hello everyone, and welcome to the first iFormulate Introduces webinar of 2017. In the next half an hour you will be given a quick guide to Hansen Solubility Parameters, which we may refer to as HSP. My name is David Calvert and I will be your first speaker today. I'll be joined in the second session by Dr. Jim Bullock, my co-founder of iFormulate, and he'll take you through the second part of this webinar. In the webinar you'll hear about, in the overview there, about why is solubility important. We'll then talk about Hansen Solubility Parameters, a basic introduction, some case studies, and then a summary and learning more. The webinar will last around 30 minutes. We know that you're busy and it is being recorded, so it will be made available to you afterwards, and you can share this with your colleague together with a PDF of the slides that you will see on the screen. If you'd like to ask questions, please use the question box in your panel. We'll try to answer them at the end, but we have muted the audience to prevent background noise, and as I say, this webinar is being recorded. So, a little bit about iFormulate. Those of you who are joining for the first time, we were formed in 2012 by Jim and myself. We've been in business for over 4 years as a company, but between us we've both got over 25 years experience of working in the formulating industries. We bring our own experience and knowledge gained across these many industries and in varied functional roles. And when we can't have the in-depth knowledge that's required for projects, we use a complementary network of associates, and you can see our webpage there at the bottom of your screen. We divide our activities into 3 business areas. In iFormulate Consult, we carry out innovation and technology consulting, mainly in formulation but also in the materials and processing areas, and these are all for clients and companies in the private sector industry. As iFormulate Strategic, we have carried out and assisted in a number of strategic projects in the area of formulation for sector bodies and associations such as the Knowledge Transfer Network, the National Formulation Centre and the Royal Society of Chemistry. And this strand today is under our iSkills banner, where we design, deliver and promote training courses and programs in formulation science and technology, and these may appear under our own banner or maybe in partnership with third parties, and we'll be we're helping the University of Leeds to organise a spray drying course in the very near future. But as we said, this webinar is one of our iFormulate skills activities, and you'll be able to find more details of that and indeed recordings of previous webinars on our website. So what are we talking about today? Well, Hansen Solubility Parameters is a tool we've used ourselves in a number of projects and found it to be very useful. But of course it's not a panacea, but we can't talk about something with Hansen Solubility Parameters, with that word solubility, without giving you, I suppose, a rather bland definition of solubility. This comes from the UPAC Gold Book, and it says the analytical composition of a saturated solution expressed in terms of the proportion of a designated solute in a designated solvent is the solubility of that solute. The solubility may be expressed as a concentration, molality, mole fraction, mole ratio, etc. I can assure you this webinar is going to be a little bit more exciting than that definition, but we did think it was worth considering at the beginning. So what does it say in those? Well, it talks about the solvent, and the solvent is really where HSP, Hansen Solubility Parameters, comes in. It helps you to look at what is the best solvent for your system. Poorly soluble is a term you'll hear often used in the formulating industries, and that refers often to water, which is an area which Hansen Solubilities can deal with, but it's not particularly as straightforward as other solvents. Units for solubility, well, we often see grams per litre or percentage weight by volume. The saturated solution is key actually in that definition, and it does talk about equilibrium, and that's an important aspect to have in terms of the equilibrium when you're determining solubility. And the factors that can influence that, of course, are temperature, pressure, and when you have solubility problems you can often solve them with particle size. Sometimes changing the counter ion and purity can have an effect on solubility. Often language is very important, and people refer to compatibility when really they're also talking about solubility. So if you have compatibility problems, this product is not compatible with the resin, in essence you actually have a solubility problem. So where is solubility important to formulators? Well, it's important in all the industries where formulation is a key enabler. They're often, obviously, in pharmaceuticals, in agrochemicals, where you're looking to deliver an active to a target crop. In coatings, solubility is important in inks, and personal care and cosmetics, obviously also important in home care. And what does it influence? Well, it influences really the efficacy of your final formulation, how that is delivered. In terms of if you can get more into your product, then obviously you should reduce the cost, and it also plays an important part in various regulations. Sometimes people talk about a partition coefficient or relative solubility, and that can sometimes be more irrelevant, and sometimes insolubility is important when you're doing something like precipitation or encapsulation. And sometimes also in your systems you do need to consider that the system is changing. So in a cream, for example, sometimes the water is evaporating, and then really your solvent is becoming actually an oil. But let's have a look at just a couple of those sectors. So if we look at agrochemicals, soluble liquids are the simplest, most traditional formulations, and here you find glyphosate, the most successful herbicide being used. In terms of their issues there, they've solved their solubility by using different salts. This is not an area perhaps where HSP is very helpful. But where HSP can be very helpful is in emulsifiable concentrates, which is a solution of the active ingredient with emulsifying agents in an organic solvent. And here there have been a number of what you might call traditional solvents being used, and the alternative solvents which are being promoted often use HSP to promote how equivalent they are to some of those traditional solvents. If we look at pharmaceuticals, most of the new chemical entities are practically insoluble in water, but as we've discussed earlier, HSP is not so applicable to those issues. But some of the techniques that people are using to solve pharmaceutical delivery can be solved with HSP. In particular, the solid dispersions, where you can use HSP to assess what would be the best polymer for your active ingredient, and when people use surfactants, then indeed HSP is very important. If we look at some of the regulations, then solubility is clearly important to comply with a number of these VOC regulations, and the move away from the more traditional, some people may say some of the nasty solvents. It also helps you also to look at polymer compatibility when you're looking at binders. And obviously solubility is important to minimize the toxic effects and to minimize the environmental impact. So how would you measure solubility? Well, those of you who've done it in a lab, you often know you just add in your solute into the solvent until it starts to take no more, as they say, or to become turbid. But there are a number of automated ways of doing this, and this is just one courtesy of Technobis, where you can look at different concentrations in a number of solvents and you can do it automatically. And you can see on this slide a graph of the type of results you can produce from that machine. So having given you an overview of solubility, the question maybe on your lips is, can you actually predict solubility or compatibility? And at this stage I'm going to hand
Unmuted.
my colleague Jim Bullock, who is going to talk you through an introduction to Hansen Solubility Parameters. Over to you, Jim.
Thank you, David. So the question here is, can you predict solubility and compatibility? And for that we're going to take you through the basics of Hansen Solubility Parameters. Can we have the next slide, please? Yes, so the kind of challenges that you may get as a practical formulator might not be measuring an absolute solubility or predicting absolute solubility to 2 decimal places, but a more practical kind of challenge you might get is, for instance, how can I predict solubility well enough to choose a new or a replacement solvent or some other ingredient which is compatible with my formulation. So it's well enough, and for a practical formulator, well enough doesn't have to mean perfectly. So very often just narrowing the extent or the amount of experimental work you need to do is justification enough for making that kind of prediction. So when we start to talk about Hansen Solubility Parameters, what we've done here is to bring in some concepts without using any mathematics, and we're trying to avoid as much mathematics as possible today. And the kinds of concepts that we'll be talking about is, first of all, interactions or forces, or in some cases, bonds between molecules. So these are interactions between solute and solute molecules. We'll be talking about interactions between solvent and solvent molecules, and we'll be talking about interaction between solvent and solute molecules. And between them, all of those interactions are important for determining solubility. Now, thermodynamics tells us that if you pull molecules apart, so you're pulling apart solute molecules, for instance, you require energy to do that. However, attractive interactions between molecules can produce energy, and systems will tend towards their lowest energy or their most stable state. That's what thermodynamics tells us. And simple observation, experimental, empirical observation tells us that like dissolves like. So for instance, if you have a hydrocarbon solvent, you can use that to dissolve other non-polar components. But how do we actually measure and quantify like? Let's look first of all at those interactions. So in the diagrams here, we've got the three types of interactions that we've introduced already. We've got interaction between solute molecules, assuming that the solute is a molecular solid. So what you might be trying to do here to dissolve something is to first of all remove those solute molecules from the bulk solute. Now here, when you're comparing solvents, actually this step doesn't matter because all solvents, the solvent's actually not involved in this step, and really this is a way of measuring the interactions between the solute and the solute molecules. So for comparative solubility, that first step is not as relevant. However, the second diagram shows you about removing solvent molecules from each other, so breaking solvent molecules apart from the bulk. We do need to know about the forces that need to be overcome to do that. And then when we're making the solution, we're dissolving the solute molecules in the solvent molecules. We are creating interactions between those different types of molecules, and we need to know about the types of interactions that are being created. So we're breaking and making interactions. Let's look at those interactions in a little bit more detail. What are those interactions anyway? Well, to cut a very long story short, the main things you need to think about at this level are three types of interactions. First of all, dispersion forces. These are weak intermolecular forces which are related to the polarizability of a molecule, hence really to the number of electrons in its electron cloud. Essentially, this is related very closely to the van der Waals interactions that we probably remember from our chemistry education. These van der Waals interactions exist between all molecules, dispersion forces. The second category of interactions are polar or dipolar interactions. So any molecules that have a degree of charge separation can form an electrical dipole. Of course, we know that electrical dipoles will attract one another electrostatically. The third type of interaction is hydrogen bonding. Hydrogen bonds are a special type of polar interaction. Some atoms on molecules can act as donors or acceptors of electrons, and typically what you have here is a partially positively charged hydrogen atom somewhere attracted to a lone pair of electrons on an electronegative atom on another molecule. Often that's seen as almost being part way to a covalent bonding. So the next question we have to consider, and the question we raised a little bit earlier, is how do we actually measure like dissolves like? How do we actually quantify this? Well, the HSP method quantifies that degree of like by describing both the solvent and the solute molecule by using just three numbers, and these are the Hansen Solubility Parameters. And you won't be surprised to hear that those three numbers relate to the three types of force that we've just heard about on the previous slide. So there's delta D or DD, the measurement of dispersion forces. There's delta P, the measure of polar or dipolar interactions, and delta H, the measure of hydrogen bonding. Now, the closer the HSP values of the solvent and the solute are to each other, then the better the solvent is for that solute. Now, we've got three dimensions here, so we have to measure that distance in three-dimensional HSP space. That sounds very complicated, but actually the maths here, and this is probably the most complicated maths we're going to get today, is quite simple. It's simply a three-dimensional distance measured in space there in Hansen space. So it's the difference of the parameters squared that gives you the relative similarity of the two components. And that can be plotted in terms of a sphere. We've drawn just as a simple circle here in 2 dimensions, but in real examples there's a sphere in 3 dimensions, and the third dimension will be dd, the dispersion parameter. So here we're plotting dp against dh. Now A, we say that A is soluble in B if A falls within the Hansen sphere of B. So there is a zone, the Hansen sphere, in which 2 components are mutually soluble within each other. And that means that the HSP distance is small for A to be soluble within B. And so very often we plot a sphere which shows the solubility of a solute within a number of different solvents. Now we've mentioned thermodynamics and energy earlier on. How are all these things related to thermodynamics and energy? Well, actually quite simply. So if we look at the thermodynamics, or the cohesive energy, or the energy of vaporization of a solid or a solvent, that can be divided up into 3 terms, into polar dispersion and hydrogen bonding terms. That's energy. We simply then normalize that energy to the molecular volume to derive the Hansen parameters. So the Hansen parameters are simply the square root of the cohesive energy density, and so they'll have the appropriate units for that. Any more detail on that is probably best found in the references to Hansen's original work that we've provided on this slide here. Now we talked about these numbers, and that's been rather abstract, so let's look at reality. What are some typical measured HSP values for different solvent molecules? And we can see how these numbers relate to the molecular structure by considering a few examples of solvents on this slide here. So let's take them in turn. So ethanol is quite a polar molecule. The OH group gives it an electrical dipole, and therefore there is a dp number of 8.8. The DH number is quite significant because you've got hydrogen bonding capability with ethanol, so we both have a donor and an acceptor of electrons in the OH group as well. Hexane, on the other hand, the second example, has purely dispersion forces and dispersion interactions. There are no dipolar interactions and no hydrogen bonding possibilities, so those parameters are 0 for hexane. For ethylene glycol, we're in a similar state to ethanol, but we've got 2 OH groups, so we've got a higher possibility of interactions due to dipolar interactions, and also a higher degree of hydrogen bonding capability with the ethylene glycol molecule. N-methylpyrrolidone, which is the 4th example on this list here, shows quite a large polar parameter, and you can see that some of the atoms on that molecule will be partly charged to give you that polar. Now, as a hydrogen bonding molecule, you can see that it doesn't have a hydrogen donor. It only has acceptor groups there, so that the hydrogen bonding number, the DH value, is modest. And the same is the case for acetone. There's a dipole and a modest amount of hydrogen bonding. So that's rationalizing, if you like, the numbers that can be obtained by measuring HSP values and then rationalizing those in terms of the molecular structure. Now we need to be quite careful when using HSP values, and here are a few watch-outs. Water is a very special molecule that is extremely small and has an extremely high hydrogen bonding capability. So that in practice, either we avoid using it for HSP at all for water, but if we have to use water, then we choose the HSP values depending on the concentration of water in the system. So we have different sets of HSP values for water depending on whether it's bulk water or small amounts of water in the formulation. Now, ionic and metallic materials can't always be predicted by HSP because the parameters that we've described there don't describe the bonding adequately. We've also got to watch out for complexes or molecular aggregates or ordering, so we've got to be a bit careful with surfactants as well. And we've got to think about absolute size plays a role in solubility and in rate of dissolution in practice. So we've got to think about that if we're not getting the results that we think. So we've placed those numbers in front of you on the previous slide, but wherever they come from, how do I actually know what HSP values I should use? Well, first of all, look in literature. There are published HSP values for very many common and some uncommon solvents and other materials like resins, polymers, and active substances. So the literature is a great source of HSP values. Commercial software such as the HSP-IP software includes extensive databases of tabulated HSP values within it. There are methods using quantitative structure-activity relationships whereby the HSP values of a molecule can be estimated from the molecular structure alone, and that's quite useful as a first estimate. But in practice, in real messy systems where you've got unknown materials or poorly characterized materials, then measurement can be very useful. So you can actually choose solvents from across Hansen space and then construct your Hansen sphere and use that to determine the solubility or solubility parameters of an unknown material by using solvents of known HSP values. And there are also methods using chromatography, inverse gas chromatography, whereby the HSP values are related to retention times in particular solvents. So we've got our parameters. How do we do the calculations that we need to select new solvents or new materials for our formulations? Well, first of all is the quick and easy but limited eyeball method. I call it the eyeball method, whereby simply looking at tables or lists of HSP values, then solvents or combinations of solvents can be selected by simply inspecting those lists and picking solvents that look to have the right DD, DP and DH values. Now this isn't quantitative and is subject to a certain amount of luck, but it can yield some useful results in the first instance. And in particular, combining solvents is very interesting because very often HSP allows you to combine two non-solvents to produce one good solvent from the mixture of the two, and that wouldn't be intuitively expected. It's possible to construct your own spreadsheet or build your own algorithms based on the mathematics of HSP. You might build a macro, for instance, and many of those calculations, such as the HSP distance that we've shown you, aren't too complicated, so that can be done. You'll need to find a way to integrate those published values into your spreadsheet system, and you'll need to, at some stage, quality assure your calculations. It's not impossible. And then, of course, commercial software, which is probably the easiest way of doing things, does all the calculations, integrates a comprehensive database of HSP values, manuals and other supports available. But of course, it costs money, not a huge amount of money, but requires some investment in software. How might I use HSP in value? Well, there are numerous applications. Dozens of applications available from the literature from many different industries. So for instance, choosing new combinations of solvents and resins. So you might want to choose a new resin for a particular solvent system or a new solvent for a resin system for coatings. You may wish to predict solvents for APIs in pharmaceuticals. You may wish to build systems of pharmaceuticals and cosmetic actives for skin delivery. You might want to match a particular mixture of solvents for solvent cleaning with an HSP match for the particular soils that you're trying to clean away. You can unexpectedly perhaps use HSP not only for things that dissolve but also for particulate actives such as nanoparticles. So you can use solvents for HSP for choosing solvents that can be used to stabilize particular nanoparticles, for instance, in organophotovoltaics. So a whole range of different applications. As we pointed out a little bit earlier, HSP is particularly useful for making use of unexpected solvent blends. So you might be able to mix two bad solvents to get one good solvent. If you're looking, for instance, to replace an environmentally unacceptable solvent, you might find two things that are environmentally acceptable on their own, are quite poor solvents, but mixed together actually make quite a good solvent. There's an introduction to HSP on the Hansen Solubility.com website there, and there are numerous publications with examples in them. Let's just pick out one or two of those examples. And here's a nice case study on plasticizers for polylactic acid, which I've taken from Stephen Abbott's chapter in that textbook on polylactic acid that you see referenced there. And the background to the challenge is that polylactic acid, PLA, is a green polymer. It's growing in importance. Some of you might know it. It's biodegradable and comes from renewable sources, so that's all good. To enhance the opportunities in the market, as with most plastics, plasticizers are very often needed. Now, ideally, of course, if you've got a green plastic, then your plasticizers should also be green. So the approach taken to look at possible plasticizers for PLA was, first of all, determine where PLA sits in HSP space. So what is actually the HSP parameters for PLA? And then, secondly, to evaluate what solubility properties are likely in common, so well-known solvents. Thirdly, work out where current plasticizers are used in and see where they sit in HSP space, and try and understand why they might not be as satisfactory as you might think they are. And then finally, to use HSP and HSP matching to select new plasticizers. So first of all, the first question on those four questions there is, where is PLA in HSP space? So what was done here was to take a test set of solvents, and these were measured together with solubility was measured, PLA in these solvents, and was measured to be either good or bad. It's actually quite a simple criteria, and good actually included solvents that didn't strictly dissolve the polymer, but actually just swelled the PLA. And on the plot on the upper right hand side, you can see the Hansen sphere. So the blue solvents were good solvents, and the red ones were bad solvents, and the blue ones all fit into a sphere in three-dimensional Hansen space, and with a best fit to DD of 18.6, DP of 9.9, and DH of 6. So you've got a modest amount of polar and hydrogen bonding interaction there. That HSP sphere is quite wide, which means that actually quite a wide range of solvents will have some degree of solubility or swelling behavior for PLA. Second question is, what are the likely solubility properties for very common materials? Well, you can see here are some solvents with a low HSP distance. So the right-hand column here is the HSP distance, and that number has to be as low as possible. In the typical examples, you're looking for a number below about 6 or 8. So you can see here some solvents that might be rather good for PLA. Many of these, of course, wouldn't be regarded as green, but it does give you an idea of what kind of solvents are in the right ballpark in terms of dissolving PLA. The third step is then to look at where the current plasticizers for HSP sit in HSP space. Well, an obvious place to start would be monomers or oligomers of lactic acid, so the lactide monomer and the oligomeric lactic acid. They have a perfect match in HSP terms, but they affect the mechanical properties adversely, so they can't be used. Now, citrates are green and have been tried, but their HSP distances are rather large. And so example there of a couple of citrates with HSP distance of above 8, and for that reason they tend to bleed from PLA. And triacetin, another one tried, actually has also rather a large HSP distance. Now, dipropylene glycol dibenzoate might be better. It has a lower HSP distance, it works reasonably well, but it's considered not green enough. And finally, polypropylene glycol or polyethylene glycol oligomers have a low HSP distance, around 4, but they show in practice problems of separation or crystallization if they're used as plasticizers. So clearly the currently used plasticizer materials were found to be inadequate, and HSP starts to tell you why that might be the case. So how might we want to select new plasticizers? Well, we've seen that PEG and lactide oligomers are potentially of interest in terms of their match in HSP terms, but they've got other problems. So what about considering an ester of a lactide or a similar molecule with PEG? And in fact, if you calculate what a 50-50 ester of PLA with PEG should be, you get DD values of 17.6, DP 8.6, DH 7.9, which has a very low HSP distance from polylactic acid, so it's a very close match. And in fact, it turns out there is indeed a patented molecule of that type, an oligomeric lactic acid, which has been capped with a short chain PEG. So it's an ester of the two, and that shows a really good match and a good plasticizer properties for PLA. So there's a real example of how you might use HSP to narrow down your choices of molecules and select new plasticizers or solvents. Just going to run very briefly through some case studies which will be shown at the HSP conference in April. So we've got some references here. You'll see links here to our website and some references to some published papers here. So we've got examples here of how HSP has been used for smart formulations of organic electronics, where chlorobenzene, which is a nice solvent for coating organophotovoltaics, but is of course environmentally unacceptable. So HSP has been used to pick binary solvent mixtures for smart formulations of OPV. As we mentioned before, nanoparticles can be looked at with HSP methods, and in fact HSP values can be assigned to the particle surface, and therefore the compatibility of those particles with the solvents can be assessed. And in fact the stability of dispersions of particles is related to the sedimentation rate of those dispersions, and that correlates very well with the HSP match of particle to solvent. And there's some nice examples from Loom which you can follow up there if you're interested. So examples of carbon black, zinc oxide, quantum dots, and various pigments. And the final example from the HSP conference here is a number of different examples actually from Daniel Schmidt of the University of Massachusetts Lowell, where again looking for green alternative materials such as solvents and resins and polymers for various different applications, showing some successes there of how HSP matching could be used to derive and find new materials. So that was a very brief run through of the practice, the theory and the practice of HSP, and how HSP could be used to select new components for your formulation. I've trailed already the HSP and mentioned the HSP 50 conference, and we're very pleased indeed to be involved in promoting and helping to promote and organize the HSP 50 conference, which is hosted by the University of York in April. You can see the details there. It's a special conference to celebrate 50 years of Hansen's parameters and includes academic and industrial presentations. It's hosted, as I say, by the University of York's leading Green Chemistry Centre of Excellence. It's got an excellent program, and amongst the highlights is a keynote address from Charles Hansen himself, who will give us a bit of introduction on how HSP were developed. And there'll also be some discussions of how the theory is being taken forward and developed and improved as time goes on. There'll also be a workshop on how to get most out of HSP. You can see the link there. And further information can be found on the conference link here. There is an early bird discount before the 15th of February, so any registrations that come in before the 15th of February will attract a discount. Abstracts are now officially closed, but we do hear that if you're interested in submitting a poster presentations are still available, so they can be followed up by the link that I've supplied there. And finally, there are also exhibition and sponsorship opportunities. The venue is excellent. It's the new Ron Cook Hub at the University of York, and there'll be a dinner at the National Railway Museum. So a very attractive conference. Hope you'll be interested in coming along to that. Finally, we're going to move on to questions. So we have the GoToWebinar question boxes here, and you've had the opportunity to provide questions as we've gone along, and we'll try and answer any of those that come in. I'm now trying to see which have come in. Yeah, there's the question that we have here, and we're running actually short of time now, but we had a question here about slides. Yes, you will be sent an email within the next 24 hours which will contain a link and a password which will allow you to access both the slides and a copy of this recording. So I'd like to finish off here by thanking you for your attention today. If you have any follow-up questions or other inquiries, please use the email address info@iformulate.biz. And if you're interested in any of our other training or webinar events, then please go to our website training link, which you can see there. Thank you very much for your attention today, and we hope to hear from you again. Thank you. Goodbye.